Module 5, Lecture B, Capstone Build. By the end of this lecture, you will be able to design a small Python project that addresses an industrial engineering problem, implement and verify a working solution using only built-in Python capabilities, and communicate project results, assumptions, limitations, and recommended next steps. Project planning. Problem selection. Choosing the right problem is key to a successful Capstone automation project. Focus on real industrial engineering needs involving repetitive work, scattered data, or manual steps that create delays or errors. A good Python solution should make the process more efficient, so begin by observing the workflow, identifying its inputs and outputs, and finding the main source of confusion or inefficiency. Choose project problems that have clear inputs, outputs, and repeatable patterns. Python is well suited for tasks such as organizing data, doing calculations, and formatting information. Avoid problems that depend on specialized hardware or overly complex systems, since they can distract from the main design work. The strongest projects are important but manageable, so the team can understand the process and improve it. Choose a project problem that clearly helps users make better decisions, save time, reduce errors, or communicate more effectively. It can be a small workflow improvement, such as automating one difficult step. As long as the data is simple, assumptions are clear, and success can be demonstrated with examples. A strong project should address a real industrial need and fit a concise Python solution that can be built and tested well. Python code problem selection. Choose automation projects by focusing on practical problems, comparing possible tasks with simple criteria, and keeping the scope realistic enough to test. A collection of industrial engineering tasks is defined for later evaluation and automation selection. It includes summarizing shift production notes into a daily report, predicting factory demand from live sensor data into a forecast dashboard, and flagging overdue maintenance work orders from a small work order list. Each task is described by its input, output, repeatability, user value, and scope risk, making it easier to compare which option is most suitable for automation. This script compares several industrial engineering problems to choose the best candidate for automation. It scores each option based on how clear its inputs and outputs are, how repeatable the task is, how much value it offers users, and how risky its scope may be. The highest scoring problem is recommended, with a short summary of its input, output, and selection score. Define project scope. Defining project scope means deciding exactly what the project will and will not address before starting detailed work. In industrial engineering, this prevents a focused problem from expanding across too many processes and constraints. For a Python project, choose a manageable piece of the issue and clearly state the process, users, data, decisions, and expected output so the result stays practical and well-defined. A clear project scope defines the boundaries that keep work focused and manageable. It states the time frame, assumptions, level of detail, and what is excluded, such as predicting failures or accounting for unexpected staffing events. These choices help clarify goals, set expectations, and ensure the project stays aligned with its objectives. Define project scope as a focused decision support tool, not a full enterprise system. It should be small enough to build and test, but meaningful enough to show how automation improves an industrial engineering task. A clear scope links inputs, processing, and outputs, such as using operational data to produce reports that highlight areas needing attention. This script defines a small warehouse analysis project focused on daily order picking times. It reviews sample orders to calculate the average picking time, identify late orders, and summarize delays by warehouse area. The scope is limited to reporting picking performance for specific users, excluding labor scheduling and route optimization. It also recommends checking the findings against a full week of data. Scope selection. Scope selection makes a complex industrial engineering problem manageable by narrowing it to one practical Python task, such as estimating staffing needs or checking production limits. It keeps the project focused within time and technical limits, using clear logic and basic data handling with built-in Python tools. The goal is focused decision support rather than a broad solution or reliance on advanced external libraries. When defining a project scope, focus on the decision the user needs to make, not just on automating a task. A practical project should target a clear, manageable outcome, such as showing when truck arrivals exceed dock capacity or summarizing defects by product and shift. Clearly defining inputs, such as text files or manual entries, and outputs, such as summaries or recommendations, makes the system easier to design, test, and verify. Choosing a project scope means deciding not only what to include, but also what to leave out. In industrial engineering projects, features like optimization or real-time data collection should be added only when they directly support the main goal and can be completed reliably. Clear exclusions keep the work focused, manageable, and testable while still showing how Python can support practical decision-making. This script compares project ideas using simple planning criteria. It adds each idea's data readiness, built-in fit, and user value, then subtracts scope risk to choose the highest scoring option. The output identifies the top project, the decision it supports, and its scope score, while noting that the scoring is a judgment-based guide rather than precise optimization. The next step is to define the chosen project's inputs, outputs, and test cases. Build and verify. Code implementation. Code implementation means turning a planned solution into a working Python program using standard features. The goal is to create clear, reliable instructions that match the real-world problem, such as processing data, calculating results, or organizing requests. Good code should make each transformation easy to trace, avoiding shortcuts that hide the logic. When using only Python's built-in features, careful program design is essential. Strings, lists, and dictionaries can support small automation tasks, such as tracking inventory or checking measurements for outliers. Functions help organize the work into clear parts, making programs easier to test, explain, and use for real-world decisions. When building a program, plan for real-world data problems such as missing files, incomplete records, or values that cannot be converted. The program should report these issues clearly rather than fail silently. Make key assumptions explicit through names and comments, and keep the solution organized and stable enough to test. This helps ensure the program solves the intended problem without creating new errors. This Python script verifies production records by creating a small CSV dataset, reading it, and calculating key metrics. It totals planned and actual minutes, counts good units, computes throughput as good units per hour, and flags any jobs that took longer than planned. It then checks that the expected number of records and total delay are correct, reporting success with the main results or failure if file or data errors occur. Test the solution. Testing a solution means checking that a program correctly solves the intended problem, not just that it runs without crashing. For small Python projects in industrial engineering, Start with simple cases where the expected answer is clear, such as verifying labor hours or sorting work orders by due date. These basic tests confirm the core logic before using more complex data, and Python's built-in tools are enough to compare inputs, processing, and expected outputs. When testing a program, include both realistic data and edge cases, because real industrial data may contain missing values, unusual formats, or extreme numbers. The program should handle these situations safely and avoid misleading results, such as misreading a day with no downtime or producing negative inventory. Check results against trusted manual calculations or past data, and use clear messages, assertions, and varied tests to confirm predictable behavior. Documenting verification makes a solution understandable and trustworthy. A good testing record explains what was tested, why those cases were chosen, and how actual results compared with expected results. This is especially important in industrial settings where software decisions can affect cost and safety. Noting limitations, such as problems with large datasets, is also part of professional verification and helps show that a tool is reliable. This script tests an inventory calculator that decides how much stock to order using demand, current stock, and a safety buffer. It compares the function's results against predefined expected outcomes, where the order amount is the remaining shortage after current stock is considered, or 0 if no shortage exists. The script reports whether each test passes, counts the successful cases, and prints a final total. It also notes that inputs must already be numeric and validated before testing. Review results. After building a Python solution, review its results with engineering rigor. Check that the outputs are not only free of errors, but also accurate, realistic, and relevant to the problem. Compare results with known data or past performance, and use engineering judgment to identify values that do not make sense. This helps ensure the solution supports good decisions instead of creating false confidence. When reviewing a Python solution, focus on the assumptions and limits behind its design. Built-in tools can automate file reading and data processing, but results are only reliable when the input data and assumptions are sound. Check that data definitions are clear, edge cases are considered, and the program accounts for practical issues such as timing, damaged stock, or delays. A good solution should also remain understandable to others. The final step in reviewing results is translating technical findings into practical insights. In industrial engineering, a Python solution should show how it improves a process, reduces manual effort, supports decisions, or reveals patterns. A clear review explains what the results mean, how reliable they are, and what actions should come next, while also communicating the solution's value and limits. This script checks production efficiency by comparing current cycle times with a historical best. It validates that cycle times are positive, calculates the average, and uses planned work time with allowances for breaks or delays to estimate daily capacity. It then reports the valid observations, average cycle time, estimated capacity, and performance gap, helping decide whether current results are reasonable or need further review with real production data. Result communication, assumptions, and findings. When presenting an automation project, explain both the results and the assumptions behind them. Estimates such as labor needs, inventory risks, or daily output are only meaningful if the audience knows the conditions used, such as shift patterns, breaks, and demand levels. Stating these assumptions clearly helps others judge whether the findings apply to their own operation. When presenting Python project findings, explain what the results mean, rather than only reporting numbers like counts or averages. Connect patterns, such as equipment stoppages or inventory shortages, to practical implications like maintenance needs, training, production risks, or supply chain issues. State key assumptions alongside the findings so listeners understand the limits of the analysis and avoid overgeneralizing from the data. When sharing assumptions and findings, use a balanced tone that is confident but honest about limits and the evidence. Explain what the project shows and where the data may be incomplete, such as whether defect data covers all shifts and suppliers. This transparency builds trust and helps decision makers choose whether to act now, collect more data, or expand the project. This script estimates production output for an 8-hour shift after subtracting 2 15-minute breaks. It checks that the cycle time observations are present and positive, then uses their average to estimate how many units can be produced in the available time. It reports the average cycle time and expected shift output, noting that the estimate assumes stable staffing and steady demand. Assumptions and limitations. Assumptions and limitations explain when an automation project can be trusted. A Python solution may work on sample data, but decision makers need to know what it depends on, such as accurate production times and consistent downtime categories. Stating these conditions is not a flaw. It helps show whether the project fits the real environment, provides useful results, and needs more validation before wider use. Limitations explain what a project cannot fully handle and where its results may be unreliable. In industrial engineering, these limits often come from poor data quality or the simplicity of a small Python program, such as missing real-world factors like worker skills, material shortages, congestion, or scanner errors. Stating these limits clearly builds credibility and shows that the project is usually a proof of concept, not a replacement for expert judgment or advanced software. Assumptions and limitations should be explained in terms of how they affect decisions, not just listed. A tool may be useful under normal conditions, but less reliable when conditions change, such as shifting labor rates or new defect patterns. Clear discussion of these boundaries shows sound judgment, preserves the value of the work, and helps identify where caution, scaling, or further automation is needed. This script creates a concise project report from a utilization checker tool. It records the tool used, sample size, estimated utilization rate, key assumptions, and major limitations, then pairs each limitation with a recommended next step. It also checks that these lists align correctly and raises an error if they do not. The final output gives stakeholders a clear summary of the findings, assumptions, limitations, and follow-up actions. Recommended next steps. In automation projects, completing the technical build is only the first step. The results should be translated into clear recommendations that explain what to do next, why it matters, who is affected, and what evidence supports the decision. For example, a downtime summary tool should be tested on more historical data before routine use, and a scheduling script should be compared with supervisor decisions to judge the value of human input. Good recommendations are specific, practical, and grounded in real limits such as time and data quality. When planning next steps, separate quick fixes from longer-term goals, and keep the explanation practical. Immediate work may include checking data accuracy, improving user messages, and making file updates easier. Longer-term plans can include system integration or expanded features, but they should be specific and testable. This balance shows both technical understanding and awareness of how the project will operate in practice. Effective next steps should make clear who owns the work, what risks remain, and which decisions are needed before moving forward. A strong project report frames the work as a credible prototype, not a finished system, by identifying missing evidence and conditions for reliable use. The goal is to help decision makers understand the project's value and move from a successful demonstration toward a dependable application. The script reports a successful verification of a downtime summary tool, tested on 30 maintenance logs, which saved 95 minutes of manual work with a 3.3% error rate. It recommends next steps, such as testing more records, adding warnings, training supervisors, and connecting the tool to a database, with each action ranked by combined impact and feasibility and assigned to an owner. It also notes key limits, including reliance on consistent log formats and lack of peak shift testing, and suggests approving a pilot after further verification. In this lecture, you learn to design a small Python project that addresses an industrial engineering problem, implement and verify a working solution using only built-in Python capabilities, and communicate project results, assumptions, limitations, and recommended next steps. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.